Okay, thank you very much, Matthew. My name is Duk-Yong Choi from Seoul National University. So today I want to talk about optical metasurface or optical metamaterial, but not traditional, but it's stacked. So optical metasurface research is around 20 or 25 years. So I think it's not more frontier, but this approach would be kind of frontier. So optical metasurface is an artificial nanostructure array with sub-wavelength unit cell and thickness. So here the sub-wavelength is very, very important. And normally it has one single material and single layer. So patterning is very, very easy. So it can replace lots of some bulky optical component, such as frequency selective metasurface, like some color filter, and some wavefront control like a lens, and it can also do polarization control like a vortex beam generation, and it can generate new color using non-linearity of material and structure. However, this kind of single material and single layer, sometimes it's not enough. So to enhance or to generate new function of some new metasurface, we are considering stacking of metal layer. So in terms of configuration, it can be both sides of substrate, or it can be only one side. So in this talk, I present what I have been done with my collaborator or sometimes customer, because I service them for fee. So here you go. So the first example is on one side, but here is one metasurface. There is some polymer gap and another metasurface, and this metasurface was fabricated by silicon. But silicon is quite high temperature material, and there's some polymer interlayer because amorphous silicon can be grown at 200 degree or 300 degree without any problem. That's why it can be done. So in this metal surface, normally metal surface is working in transmission mode or reflection mode. But in this example, we are using both sides. That's why it's called full space metal surface. So it can transmit in TE mode, in forward direction and backward direction, but it can reflect in TM mode. So MS1 can reflect doing one function, and from this side, MS2 function another side. So in the experiment, so TE goes through and make this kind of some complex vortex beam generation, going forward or going backward, it's the same. But for the reflection mode, TM mode, it reflects and make this kind of some deflected light, a little bit different angle. So using this kind of performance, we can generate 3 hologram images. So one for transmission, it can make a heart shape in transmission and this way as well. But in the reflection mode, one reflection make a star shape, another one is make some triangle shape. So this project is still going on. So another one is on both sides of substrate. So in this project, we wanted to make a beam scanner for LiDAR application. So for solid state LiDAR, so normally LiDAR has some moving part, but we wanted to remove this kind of moving part. So for doing that, we need some light scanner. We apply 2 metasurfaces. One is here, red one is some concave, and another one is convex lens. So light is going in and it converge first by convex lens and diverge. So we demonstrate this exit angle is 3 times bigger than this incidence angle. So using this, we integrate with the silicon nitride waveguide for LiDAR application. So here, all the light goes through it and branches in the MMI splitter. And then there's some grating coupler, looks like this. So all the way wave goes in, and on this grating, it goes up, emitted outside. But by changing the wavelength of this input light, it can slightly scanning. So the scanning range is about 7 degrees when we change the wavelength about 100 nanometer. So it's not enough. So when we integrate with this double-sided metal lens on top, it can easily cross by 3 times. So 21 degrees. And then we can input here as well as input the other way around, then we can easily 2 times more. So 42 degrees may be usable. So the previous example is just putting metal lens on top, but in this project, we want to all integrate on the waveguide directly. So this platform is a silicon nitride waveguide and silicon as a metal atom or metal surface. So by changing this period and the shape of this structure, we can easily make some converged or focused light above the waveguide, or different polarization can emit it in different direction. Okay, so this is also the both side, but we use this both side metal surface for retroreflector. So retroreflector is some device reflect light back to origin. So regardless of this incident angle. So reflect the incident angle is here, but reflect this way. So the structure is, this is convex lens and concave lens, and there is some aluminum reflector. So thickness of this silica is very, very important because the focal length of this convex lens and concave lens is exactly matching with this thickness. So the structure is, the front surface is the amorphous silicon again, and 1 micron tall structure. On the back side is the same, but different phase profile. So using this little reflector, we use it for free space communication. So here, 1010 signal is going in, hits the little reflector, and we detect the reflected light. So by changing the little reflector angle, we can see up to 25 degree angle, this little reflector works well, up to 9 gigabps speed. Okay, so all the examples so far was amorphous silicon, but now I changed the gear to titanium dioxide, TiO2. It's for mostly visible application. But titanium is a very good optical material, but it's very difficult to make a vertical shape or a high aspect ratio, some nanostructure, because it's very, very hard to etch it. That's why this kind of some new method like lift-off, dielectric lift-off, sometimes Damascene process. So in the process, you make this kind of hole using electron beam lithography process, and then ALD process, atomic layer deposition. The good thing of ALD is it's layer by layer process, and after filling this gap hole, the top surface is become flat. Then etch it to this resist layer, and resist can be removed by oxygen plasma easily. So this would be one of the most difficult fabrication so far. So titanium dioxide, this kind of structure on both sides of silica substrate. So my friend asked me to make it, and the thickness of silica is 1 millimeter, but the pattern here, alignment accuracy is below 10 micron. So anyway, long story short, it was made, and as you can see, here is the front surface, and here is the rear surface. It's around 5 micron range it can be made. And this is the front metal surface, top view, and this is tilted view, and this is the back side. the height of this titanium dioxide is about 600 nanometer, and up to 100 nanometer it's quite stable, but below 100 nanometer, sometimes it's fallen like this. So this is some stability issue in this small range. Okay. If you are making some titanium dioxide single material to make a color filter, reflective index of titanium is a little bit high, 2.5-ish or something. So it always has this kind of some higher order mode. As a consequence, the color is not pure. By removing this kind of higher order mode, we design this kind of structure. So titanium dioxide is sandwiched by silicon dioxide and silicon nitride on top of silicon dioxide. So it's a sandwich structure. So refractive index is gradually changed from 1, 1.5, 2.5, 2, and 1.5. So gradually change to make only one single mode. So in the fabrication, on the glass, 3 layer is stacked together, all together, and patterning and etched all at once using CHF3 plasma. So it's not a big deal. But anyway, the color looks really good. I'm quite happy with this result. And as you can see from the gap and the period, it changed the color. And it also occupies lots of some big color map. So in conclusion, I talk about few layer metal circuit. It's a stacked one. So there's some aluminum nanostructure or amorphous silicon doublet or titanium dioxide doublet or high purity color filters. So this kind of some metal, few layer metal surface can enhance the efficiency and controllability as well as some generate new function. With that, thank you very much.
Any questions? It's available after the session if you need to talk.
Yep.
Thank you again.
Okay, thank you.